Today we're talking about planets and Kepler's laws. Kepler's laws are about planets. So everything, as you can see, is interconnected, interrelated. Where did the idea of the planets came from first? Well, obviously, ancient Greeks, because they were observing the universe and checking what's happening on Earth and then out there. So what they noticed is that most of the stars, they were visible at night, and what they thought is that there was a ball kind of like this, and the stars were attached to the ball, and then it just moved, so the ball moved around, so the stars, so they would see, and then the ball would turn, rotate every day, so they would see the stars in the same positions every single day, except five stars that they called wandering stars, or in Greek, planets. So, planets is Greek for wandering because they were not in the same positions every single day. And I must mention that they were observing them with their naked eye because there were no telescopes. Telescopes only appeared around 1600s. So obviously back then they thought that the Earth is the center of the universe, right? And then the stars are moving around the Earth. So that means that the idea that the Earth, everything moves around the Earth, is called geocentric view. We already know from geometry, geography, right? Geo is Earth in Greek, so that was geocentric view. And then later on, Ptolemy, uh, so the Ptolemy was developing this idea, and later on, it was developed that actually we have a heliocentric system. Helios is sun in Greek, so everything moves around the sun, including, and the Earth is just one planet, one of the planets between Venus and Mars somewhere. So that idea was proposed in ancient times, but it was not very popular, and it only took off during Renaissance, in Renaissance Italy in 15th century. So that is when Nicolaus Copernicus, um, worked on it, and then we know that Galileo worked on this as well in around 1610. And in around 1610 he had a telescope developed, which had a 30 times magnitude, so he was able to see different planets. He observed that planet Jupiter has a moon, um, like us. He observed that Venus has phases like our moon, and it was not easily explainable by the Ptolemy system. So that is kind of like the idea. So planets, right? So planets, fixed planets, were on the ball and it was rotated. There were five planets were wandering, stars. Sorry, stars were on the ball. The fixed stars. The five stars that were wandering stars, they're called planets. Geocentric view, and then heliocentric view later on. Okay, so that is where Kepler comes into place. So Kepler, around 1600s, that was before Newton's laws. Kepler, his name is Johann Kepler. He's German astronomer. He worked out a detailed description of the motion of the planets around the sun, and I'm going to show you some diagrams so that it's visual. We can visualize what's happening. One second. And I'm back. So I put here the name of Johann Kepler so that you can see how it's spelled, Johannes Kepler, from 1571 to 1630. So what he was doing is he was examining a lot of data that was collected by Tycho Brahe without a telescope, but he had a lot of data of where the planets were. And what Kepler observed is that most of the planets, they move in an elliptical, well, sorry, all the planets, they move in an elliptical orbit, which sometimes is nearly circular. So from math, you should know that ellipse is a set of points such that each point on the ellipse is equidistant from the sum of the distances from this point to two foci is the same, is constant. right? So the circle is a specific case of an ellipse when the two foci are actually squished together and they become just one focus, which we call the center of the circle. So in this case, what we can see is that our planet P, the distance from focus 1 to planet P and from planet P to focus 2 is the same. So the planet moves around the sun in an elliptical object. Sun is one of the focus, one of the foci. So sun is the focus. And then the second focus is, well, somewhere else. Okay, so that is Kepler's first law. Now, the second law says that the planet moves. So here we go. Planet moves in such a way that if we have an imaginary line drawn from the sun to the planet, it sweeps out the equal areas in equal periods of time. So if the planet changes from, say, in one day from point 1 to point 2, then this area is going to be the same as if the planet moved from day 3 to, well, from some day from point 3 to point 4, right? So there's that, let's say the planet moves over here on one day and over here on one day, or maybe it's 1 week, maybe it's 1 month, who knows? But it's the same period of time. So those two areas are going to be the same. We know that when the planets are closer to the sun, they move faster. So that's why we see that it covers bigger arc. And when the planet is furthest from the sun, it moves slower. So this arc is a little bit smaller, but the areas are the same. All right, now let's talk about Kepler's third law. So the third law is more mathematical, involves an equation finally. So it says that the ratio of the squares of periods t, so T1 over T2, so ratio of the squares, or square of the ratio, same thing, of any two planets, so planet 1 and planet 2, revolving around the sun is equal to the ratio of the cubes of the mean distances from the sun. Okay, I'm going to explain what mean distances are in just a moment. S1, S2, but that is cube. So the ratio of the periods, and those are the ratio of the mean distances. So I'm going to scroll back to this diagram, and I did not mention it before. So this is the mean distance. So the mean distance is half of the major axis. In ellipses, we remember that major axis is from point N to point M, and the mean distance is half of the distance from this axis of symmetry to like point M, right? Or from axis of symmetry to point N. So it's half of the distance from N to M. That is S. This can be changed, so we can obviously, it's like a proportion, so we can manipulate it a little bit and we can write it down in a slightly different form. We can say that S1 cube over T1 squared has to be equal S2 cube over T2 squared, which means that S cube over T squared is the constant value for the same planet. And I'm going to show you the table that actually shows us those values, and we will see that they're very, very close to what he proposed in year 1600 or so. So here's the table that I was mentioning for different planets, even including Pluto, even though we know it's not a planet anymore. So from we have mean distances, so S, we have period, and then we have our ratio S cubed over T squared. So look at this, all those values are very, very close. And that's pretty much, I don't know, it's fascinating to me because he was able to propose this back in time, hundreds and hundreds of years ago, without the technology that we have now. All right, an example. We are going to try and find Mars. Where is Mars? So Mars's period, so the year, Mars's year, was noted by Kepler to be about 687 days. So those are Earth days, which means that it is about 1.88 years. If we calculate in Earth's years, we need to figure out the mean distance of Mars from the Sun using the Earth as a reference. So that's what we're going to, here's how we're going to calculate it. So first of all, we know that the distance from Earth, solution. sorry, solution. So the distance from Earth to Sun is 1.5 times 10 to the power 11 meters. You can Google it. So that's the distance. That's the known distance. So the distance from Mars to the Sun, we're going to label it as from Mars to the Sun, right? That's the one that we need to find. Determine the mean distance of Mars to the Sun, and the the distance from Earth to the Sun. That's going to be this one. So that's going to be S ES. Okay, so that's our distance. All right, so now from the Kepler's law, we know that S ms over S ES, it has to be, and all that cubed, right? It has to be equal period of Mars over period of Earth squared. That's an E, right? How do we get rid of the cube? We have to take the cube root, aka raise it to the power 1/3. So you're going to get SMS over SES is TM over TE to the power 2/3. Okay, specifically for Michael, this E is a lowercase, it's a subscript E, so it's not TE. Okay, and now we can plug in our TM, which we said was 1.88 years. That's the period of Mars. And the period of the year, I guess it's going to be, I don't know, such a hard number to figure out, 1 year, right? And then to the power 2/3. And if we calculate everything correctly, we are going to get 1.52. So that means that Mars has to be 152 times Earth's distance from the Sun. So we have to multiply this now times 152. So the distance from Mars to the Sun is 152 times 1.50 times 10 to the power 11 meters. That is going to give us 228 times 10 to the power 11 meters. Ta-da! Let's derive Kepler's third law. We are going to do it for actually a circular orbit, not an elliptical orbit, just to simplify the calculations. And that was done later in life by Newton after using Newton's law of universal gravitation. So we know that sum of all the forces has to be equal m times a, right? And the gravitational force is m1 times m. We're going to choose mass of the Sun as one of the masses because the planets are moving around the mass, and it has to be r1 squared, and that should be equal m1 v, that's 1, v1 squared over r1. Okay, so that is for a planet of mass m1, so some planet. All right, so now, so the mass is is the mass of some planet, r is the distance from the Sun, and what we're going to do is tie it together with the period. So remember another formula that we had when v1 was equal to pi r1 over period 1. I didn't mean to put 1 over there. It's 1. It's not to the power 1. R1. So let's go ahead and substitute this guy instead of v1 squared. And this is what we are going to get. So g m1 mass of the Sun r1 squared equals m1. Now squaring this, we get 4 pi squared r1 squared over t1 squared, and then this r1 is also there. Now this r1 and this r1 squared, they cancel out, so you just have r sub 1 in the numerator. And then now we can rearrange this to get the following thing. So we can see that the masses will cancel out. Let me use a different color. So the masses will cancel out, right? R1 and r1 squared, those are going to become r1 cubed. So now you have, and I'm going to divide t1 squared by that. So t1 squared over r1 cubed is going to be equal 4 pi squared. Okay, I'm dividing this guy by this guy. So it's going to be this over this part, over g, over g, and then mass of the sun. All right, so that is derived for the planet, whatever, for the first planet. But look at the right side here. 4 is a constant, pi is a constant, g is a constant, mass of the sun, it's mass of the sun, it doesn't depend on the planet. So if I were to derive it for another planet, I would get pretty much the same formula. I would get t2 squared over r2 cube equals the same thing, because it's the same exact logic, g ms. Well, what does that mean? That means that my two parts of the equation, this part and this part, they have to be equal to each other. So t1 squared over r1 cubed has to be equal t2 squared over r2 cubed, which means in turn that t1 over t2 squared has to be equal r1 over r2 cubed. And that's exactly what Kepler derived or explained many years ago, before Newton. With that said, we are looking into a new example. And our new example is about the sun's mass. So now we know the Earth's mass, and we're going to determine the mass of the sun. So determine the mass of the sun, given that the distance from Earth to the sun is 1.5 times 10 to the power 11 meters. So we know that the period solution. So we know that the period of the Earth is 1 year. We are going to convert it into our C units. So we would have to multiply 1 year is 365 days. Okay, and a quarter. Let's do and a quarter. 365 and 1/4 days. We know that each day has 24 hours per day, and each hour has 3,600 seconds per hour. So once we multiply all this, we end up with the period of Earth being 3.16 times 10 to the power 7 seconds. And then now we will solve our equation, this one, for mass of the sun. So we're going to use this equation that we derived, and we're going to use it for the mass of the sun, because we know the period, we know the distance, and then all those are constants. So from this equation we can see that the mass of the sun will have to be 4 pi squared r cubed. Between radius is the distance between Earth and the sun, and then we have to divide it by g, and then by t of the Earth, and t it was squared. So now we just plug in our numbers. So we have 4 pi squared, then we have 1.5 times 10 to the 11th meter cubed. G is 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared, and we're multiplying it by 3.16 times 10 to the power 7 seconds, and that is squared, 3.1616. And once you multiply this using your calculator, you can pause, you can try to multiply it, and then if you do it correctly, you should get approximately 2.0 times 10 to the power 30 kilograms. So that is the mass of our sun. We know also mass of the Earth, and we are going to stop here for now, and then we will talk about some other planets next time. So that's it for now.